I have the record for most of the slides because I'm afraid bad news. So I'm going to go into a bit of detail, as Jesse has, on some of the function calls. There's no code as such. I'm going to try to go reasonably quickly. So if you're confused, please try to look obviously confused and I'll slow down. If you're bored, please try to look obviously bored and I'll try to speed up a bit. If I start yawning, it's not because I'm bored, it's because I've been awake since 5:15, so please just look cross at me and I'll keep you awake out of stress. Okay, so framebuffers. So we've heard a lot about, generally speaking with Vulkan, the way that it's intended to make use of the GPU more efficient from the CPU's perspective. So as Michael was saying earlier, we have ways of generating lots of work using multiple GPU calls, writing to separate command buffers. We've got the ability to reuse those command buffers, which stops the CPU having to do anything at all. And you can reuse those command buffers across multiple frames or multiple submissions, potentially. We've got direct control over memory management, which is intended to make sure that you're not waiting so much between GPU calls. And you've got proper control over when the shaders are happening, partly through pipelines and that level of control. So the message we've had from a lot of people so far is that the way that Vulkan is intended to help is to reduce the amount of load on the CPU side and keep the GPU as busy as possible. But it doesn't necessarily help if you're already stuck on the GPU side, because there's no magic and your GPU will already go as fast as your GPU is going. Except that's not always the case. So there are some things in Vulkan that are intended to make things go a bit quicker. And one of the problems with GL is that it was basically Iris GL. It was designed for how Silicon Graphics imagined everything was going to work in the 1990s, and that's not really how modern, particularly mobile hardware works. So the way that mobile hardware is being designed is specifically intended to reduce the memory bandwidth, which is the biggest problem that we have in mobile, and therefore the mappings that we have between GL and GLES and the way that the hardware works isn't quite perfect. The drivers do a brilliant job most of the time, but it is only most of the time. So I hope everyone here knows about tile GPUs. I will do this very quickly just in case. Bandwidth is the problem. So you take the scene, you throw it at some binning hardware or something, which splits it up into regions of this screen and works out which primitives touch which areas of the screen. Then you render each of those regions of the screen internally, effectively. And by having on-chip memory for those regions of the screen, it avoids you going out to main memory every time, and that makes everything go nice and fast. So you have nice, fast on-chip memory, and you don't have to worry about your tiny little external bus to deal with your low power RAM. So you can avoid, one of the main reasons this is efficient is that you need quite a lot of data for each pixel when you're rendering, but you don't need it all the time. So for example, you need Z buffer and stencil buffer to be able to do your calculations. You need to render at full screen, more than full screen resolution in order to get multi-sampling. But when you're actually rendering something, you only care about the final downsampled version. You don't need the Z, you don't need the stencil, you don't need the original resolution image. So you only care about the tiny little version. And we can throw all the other two. And hopefully you're doing that in GPS. So the other things, you don't need to load anything from previous frames, so you're not pulling data back out of memory to continue rendering. But sometimes we actually do need the results of some previous rendering in full detail. So an obvious case is shadow maps, where you need to produce the Z buffer before you can start accessing it. You can do environment maps, you can be rendering the entire scene as a bloom image for doing HDR effects. But the good news is that you can often get away with lower resolution or some other form of reduced bandwidth when you're doing that. So they're not huge, they're not quite such big bandwidth pools as the main frame buffer is. But sometimes you actually do need to do all this rendering at the full resolution of the frame buffer. So hands up if you've used deferred rendering. Cool. Okay, in that case I won't make people stick their hands up to say they don't use this. So that's one example where you need to write to lots of intermediate data. Deferred lighting, similar problem, more intermediate passes, possibly less data at any given point. Transparency, again, useful to write to more than one lot of data when you're trying to resolve what transparency is supposed to look like. Tone mapping, another thing where you might want to render everything and then do tone mapping afterwards. So how do we want to implement those? The most simple case, you can just render to each of those intermediate buffers separately. That's a really bad thing to do, so that there is a bit more of a cost for using geometry on the timeline. It might not be very much, but generally speaking, because you have to do something every bit, the cost is a little bit more. And if you're going to go over the scene multiple times, once for each of these intermediate images, then you're going to have a problem that you've effectively processed more geometry. That's not really a big problem here, and even immediate mode renderers don't like you doing this kind of rendering, where you have to process everything repeatedly. So the way you get around this on a desktop system is you use multiple render targets. You write out to multiple frame buffers in a single pass. And while that reduces the amount of geometry you have to process, you're still writing all of this data to external memory, which is fine for a desktop chip that's an immediate mode renderer with fast external bandwidth, and not really very good for mobile. The other thing is that because you're writing to more stuff from one shader, you're putting more requirements in the capabilities of those shaders, so that can potentially slow things down a little bit as well. So as I said, that's what you might expect in a desktop system or in a console. So there are ways of doing this on timers. Now, pixel local storage came from ARM, so I think we can mention it here as a friendly thing. The idea is that you're doing the rendering for all of these frames, but you're only storing the value for the tile that you're currently working on, because those are the only pixels you care about, and you pull them back again when you need to consume that to do your final render. But it's not that portable, although it is implemented on quite a few people's hardware now. It's not very practical on a desktop system, which means that probably if you're doing debugging on a desktop system, it won't work. Exactly how much capabilities there are for pixel local storage is variable, so you need different fallback paths according to how much data you're actually trying to use. And the driver doesn't know what you're doing, so it can't do anything to optimize that part. And there are also some restrictions on exactly how you access that memory. So it's very effective, but it is just an extension, it's not available everywhere. So how does Vulkan go about this? So there is far more explicit support inside Vulkan saying how you're going to be using your memory. And the idea is that if you explain everything in advance to the driver can try to help you out. And that mapping is complicated if you're controlling it yourself. So, as we'll see, you have to give quite a lot of information to the driver for it to work this out, but on the other hand, if you were trying to handle all possible hardware when you were implementing this yourself, you'd still have a lot of work to automate, so please don't cry too hard. So, we start out with what a render pass is, and the idea is that if you have a series of dependent operations, then they should be grouped together into a single render pass. So if you have your deferred lighting thing here with multiple sub-stages, because they're all rendering to the same resolution frame buffer for the final output, they should all be grouped together. And you do have the restriction that all of those images are the same size. And that means that for a tiler, for example, things can be broken down so that the work done within a pass is handled within one tile for all of these, potentially. So a render pass has subpasses in it, and the subpasses correspond to the different stages of operations we're going to be giving. And those subpasses work on attachments, which are the image views that we were talking about earlier. So in this case, the intermediate Z values, normal values, and that kind of thing are all stored in attachments. And you have a dependency defined between the subpasses to say which of those attachments are going to be used by one subpass and which are going to be output by others. So the render pass itself just describes the shape of these operations that we then use use that to create a RenderPass instance that can then be put inside a command buffer. And some renderers will need to schedule things according to RenderPass, so you have to group everything for graphics inside RenderPass. Okay, code, sort of. So if you are creating a RenderPass, the way Vulkan tends to do things is you have an object that you hide all of the description stuff into. And in that case, the object that you use to create a RenderPass has attachments, a list of attachments that are all the images that you're going to be using. It's just the descriptions of them, it's not the actual attachments at this point. The description of the subpasses that you're going to be using, and all of these in a set, and the dependencies between the subpasses. And then you create a RenderPass and you get a RenderPass out, which we'll show you how to use that in a minute. So, reminder, a RenderPass is just a template that describes how you're going to be using the RenderPass, and then you'll instantiate that inside a command buffer later on. Right. So, the attachment descriptions. That's only talking about the format, my favourite topic, and number of samples in an attachment. Talks about what happens when you try to load the attachment, and there are some flags to say that you want to preserve the previous content that was in memory if you wanted to load that back in. More likely for a child renderer, you can say you don't care what's previously there because you're going to render over all of it, and you can also clear it. And when you're writing something out to an attachment, you can either say you're going to store, or you can say actually you're not going to keep that after the RenderPass is finished. The subpasses have a description of the attachments that are associated with that subpass, what they're outputting to, allowing for the fact that they could be handling anti-aliasing, and also the list of the attachments that you're not going to modify during that that subpass, so that you can have an attachment that will be preserved for use in the later subpass. There is a diagram coming, I promise. And subpasses are in order, so you can refer to them by a number later on, and they will refer back to previous subpasses. Finally, subpass dependency. So you can say for an attachment whether it's used, how it's behaving between two subpasses, what the source of it is and the destination is, and which stages have execution requirements between those subpasses. Yes, please go with the spec for this, but this is a useful input for creating everything. So we've created our RenderPass. To actually use it, we need a frame buffer, and a frame buffer includes the attachments, which the real attachments this time, the image views that are going to be used to be written to in the subpass. So there's a create info again, and it has the RenderPass to say what you're working with, and there's a list of attachments that are associated with it. And there's also a size specified at this point. Okay. So when we're using the RenderPass that we've created, there's a vkCommandBegin, which goes inside the command buffer. So if you're new to Vulkan, anything with vkCommand is something that gets inserted into a command buffer. And so that takes your RenderPass template that you've already defined, and you turn that into an instance that's actually being used inside your RenderPass. And there is a BeginInfo, again, stored in the subproject, that defines the parameters for that. Okay, so diagram, I promise. So you'll have your attachment descriptions saying what the formatting of the use of those attachments is. You have the subpass descriptions, which says what attachments are being used by each subpass. You have your dependencies between the subpasses, saying what inputs and outputs are being used by each one. And all of those are linked from the RenderPass creating frame. Pass that to create RenderPass and get a RenderPass object out. Then when we're trying to use this, we have image views that point to real memory applications. We pass that into the FrameBuffer create info, and use that to create a VkFrameBuffer. those are both referred to in the RenderPassBeginInfo. You also need a command buffer to execute on, and you pass all of that into the vkBeginRenderPass, and magically you started using a RenderPass. So don't let anybody tell you Vulkan is complicated. Fortunately, the good news is that you can use a lot of this stuff between different operations, so you don't have to set it up absolutely every time. Yes, I was slightly scared when I first drew this, but please don't be scared of the scaffold. So, how do we actually render something? We need to allocate a command buffer, which we've had a bit of discussion about already. Then we need to begin the command buffer and start actually doing some work. We've created a command buffer on the right. You need to begin a render pass to actually do any graphics rendering inside it. And then you can start doing draw operations or setting up pipeline stages and other excitement like that. End the render pass to say that you've finished doing operation on one sequence of images. End the command buffer to say you've done all of that. And then you can pass the command buffer into the command queue to actually get some work running on Vulkan. If you wanted to have multiple render passes, so I'll get around that for this one because it's a slightly rarer case, you can have more than one render pass inside a command buffer. You're not restricted to one-to-one mapping. If you wanted to write to multiple targets from one command buffer, then you can do that by having multiple render passes inside the command buffer. So one reason you might want to do that is to have decide that you're going to write to a shadow map and environment map for an object and have a command buffer set up to do that, and you can call the same command buffer to do that every frame. The one complication is that it does have to be the same targets. You can't. There's no way of mapping from the command buffer to write to a different output each time. So you can't easily do that to something like a frame buffer because you probably wanted to point to a different frame buffer output each time. And that's because the VK frame buffer is inside the RenderPass instance. So, as I was saying, we have two issues there. We have if we've got two different render passes, they're outputting to different places. So nothing gets held on the chip. It's all being written to off-chip memory conceptually. Or at least there's no logical connection between them. And if you've got this command buffer, you've got no way of pointing to a different render target. So, as I say, you can't double buffer image outputs or anything like that. We'll come back to the second problem. The first one we'll deal with now. But sometimes, particularly for things like the shadow map environment, in that case I was just talking about, that's still enough to be useful. So, what if you wanted to have more than one subpass? So you start in one subpass automatically. So a render pass always has a subpass. And the way you do to the next one is just to call vkCommandExecuteCommands, which puts that on the command key. And with the dependencies that you set up beforehand, you can say what the connections between those subpasses is. So because you're still within the same render pass when you're trying to do this, hopefully all of the memory accesses for the connections stay on chip. And it'll fall back gracefully if it can't, we hope. Quick example of functions for doing that. You've got the creating the command buffer as before, create a render pass, you start doing your rendering, then you switch to the next subpass, do more rendering, end the pass, and the command buffer, and you can submit it. So it's not that much more complicated than doing normal rendering with code. So fortunately we had a bit of a discussion of this earlier. Since this was helpfully not described in the same place as the Vulkan spec as everything else, I thought I'd write it down here. The way you access the contents of the previous subpass inside a sphere shader is an op image read, and you have this mapping, and from the GLSL extension way of describing that, you have a slightly more readable version that you may recognize looks quite a lot like pixel with storage way defining the same thing. So one aside, if we're keeping all of our intermediate memory accesses on chip, then hopefully we don't need to actually allocate memory for them anyway. So you do theoretically need to do the allocation anyway, just in case you're on something that's not a tiler, or if the tiler fails to cope for some reason. But it's a conceptual allocation, and by telling the driver that's what you're planning to do with that memory, you won't necessarily get anything allocated to it unless you absolutely need it to. Sorry, unless it absolutely needs to. So there are some flags for vk-create image to say that you've got a lazy memory committal. And so if you have a transient attachment and the tiler can keep everything on chip, then it won't allocate corresponding memory for it. So that's what subpasses are. The idea is that you've told the driver what you're about to do, so it can shuffle things around for execution order to try to make sure that the operations happen efficiently and it makes the best use of object memory. I'm guessing here you could potentially mess with the tile size in order to work out how much memory is needed for the intermediate buffers you've got. You could do some resource balancing. Most important thing is it will fall back rather than you having to worry about this. So if you wanted to use more resources than were available in the pixel local storage implementation you were working on, you'd have to write a separate code path yourself. With subpasses, everything will magically work for you. The hardware is probably doing pixel local storage on a tiler, but on an immediate mode renderer, it's probably doing multiple render targets or something like that. And it does work on immediate mode renderers, so your desktop debugger will still work, and you don't have to have a completely different pass when you're trying to debug your code. So this is one of the rare cases where pixel local storage is actually more explicitly saying what's going on than Vulkan is. Normally Vulkan, you have to tell it exactly what to do, but this time you're just telling the Vulkan driver to sort out the problem for you. So there may be extensions to offer even more control, but it's very useful to have this portable mechanism for them. So we've had a brief talk about secondary command buffers, well, we've had a more detailed talk about secondary command buffers from my talk. I'm briefly going to talk about them here and how they work with subclasses. So there are two kinds of command buffers when you create them. The primary command buffers are the ones I've been showing so far. You can have a secondary command buffer as well, and that contains things that are going to be invoked by the primary command buffer. So when you begin a command buffer, there is a way of saying in the secondary command buffer that you're going to inherit information from the primary, and that includes the RenderPass and the subpass that you'll be on when you're doing that. You can optionally pass through the frame buffer to say what actual destination you're writing to. That's optional, which means you can change the frame buffer in the secondary command buffers. So just to clarify that, you need a continue bit because you can't start a RenderPass in the secondary command buffer. You have to say you're inheriting things. You can do other things in the secondary command buffer, for example, compute shaders and the other kind of things that Michael was talking about. But if you're doing graphics rendering, then the RenderPass that's used by secondary command buffer comes out of the primary. So why do we need to specify the pass for when you're generating the secondary command buffer? That's because the operations that are being performed by the GPU in the secondary command buffer will depend on things like format, so you need to set all that up. And as I said, the frame buffer is optional, so if you provide it, then a fast path might happen, but otherwise you have the option of having the secondary command buffer able to work with multiple frame buffers. Right, so as Michael said, you can't submit a secondary command buffer directly. The point of a secondary command buffer is that you execute it from a primary command buffer. So you have a vkCmdExecuteCommands in the primary command buffer that takes as its parameter the secondary command buffer that you already created and links back to, so it invokes that indirectly. Go back there for a sec. So what that might involve doing is patching addresses, for example, in the secondary command buffer. If you have specific addresses in your shader or your state that says where the textures that are being accessed exist, because you can change the frame buffer between the recording of secondary command buffer and it being used, the primary command buffer might need to go through the secondary command buffer that it's using and make changes there. But hopefully it should be a lot quicker than recording the secondary command buffer's worth of data from scratch. So you do the begin command buffer and the primary command buffer, create a render pass. There's the command execute commands that calls the secondary command buffer. You might go to the next subpass, and so on. So again, the actual code for invoking this isn't that complicated. Most of the complexity involved in setting up the data structures for it. So command buffer creation can be a bit slow. Effectively, compilation can happen, as Michael was saying earlier. This does happen in GLES. It's not that Vulkan is slow. But the thing about Vulkan is that you get some control when all of this is happening. So by creating secondary command buffers on different threads, that means you can spread the work across multiple CPUs, and there are lots of multiple CPUs out there in friends at the moment. And the idea is that the primary command buffer that is just doing command execute commands should be relatively lightweight to construct. So it's still not necessarily directly on the rendering path. It shouldn't slow things down too much, even if it is slow. But the idea is that all it has to do is patch a few addresses at worst. So hopefully that's an easier thing to avoid being a bottleneck. Right, this is supposed to be a talk about parsers, but I'm not talking about local command buffers. The render parsers are within a primary command buffer, and the command buffer has to do the configuration for the GPU with the actual VK frame buffer. So it needs to set up actual memory pointers and that kind of thing. Rendering happens in the render pass, so if we want that rendering with on-chip accesses to use secondary command buffers, then you need to stay inside the same render pass, which is defined in the primary. So because we can't efficiently generate the primary command buffer with multiple threads, because as Tom said earlier, there's it's a list that you're tacking things onto the end of. The way to do that is to build the secondary command buffers in parallel and then refer to them from the primary command buffer with a relatively lightweight operation. One quick aside, while you're in a subpass, you can either render stuff directly, which is in line with the example I showed earlier, or you can invoke subpasses. You can't do both at once. And that's defined at the time you begin the render pass. Okay, again, putting things out of Microsoft. So you can also reuse command buffers. If you're reusing a command buffer, then you probably wanted to change what frame buffer it's going to work with. So I mentioned that for the primary command buffers, you can access the same, you'll be accessing the same image each time. Sometimes that's all right, sometimes it's not. But if you do want to access different outputs, you'd have to re-record the command buffer. Or if you're lucky and you're just alternating between a few frame buffers, then you can just record the command buffer a small number of times and repeatedly use that. That's not a very general solution. The general solution is to use secondary command buffers. And as I was saying earlier, you don't need to use the frame buffer that was available at the time everything was set up in order to, at the time that these secondary command buffers invoked. So there's a compatibility. You can consider they have to be alike enough that the secondary command buffer will still work with it. So you need the same number of formats, you need the same subpass count, that kind of thing in the secondary command buffer. And then you lightweight generate a primary command buffer with different outputs, and then you can inject secondaries from that. And as I was saying earlier, you may have to patch addresses or something like that. The secondary command buffers just exist. Primary command buffer invocation of them should be fairly lightweight. So the total amount of work you're doing is reduced, and hopefully we can see that in the applications down there. So you may come out of this thinking you've got all these cool effects you can do. Actually, you can't do quite a lot of cool effects at the moment still, because you're only allowed to access the pixel you're currently working on. So remember that a tiler is only working within one tile, and if you wanted to use that pixel to access that pixel's value, in order to keep doing work, it would be in a different tile. It wouldn't be where you get it. So you may have a problem for dealing with that. And at the moment, the workaround is write everything out of memory, the thing that we would try to avoid. So we really don't want to do that. There are other ways I'm sure you can all think of fixing this. We've thought of them too. We're working on it. No promises. Right. So wrapping up with this one. RenderPass is a fundamental part of the Vulkan API, and we're expecting people to do modern-style rendering operations with it. By giving the driver more to work with, that means that the driver has more information to do your rendering, to do a better job of your rendering workload. And because it's doing the work for you, remember that it's helping you, so please don't grumble too much about the amount that you have to type in order to make it with it. And there is some flexibility in here for the drivers to get better, so please don't expect first-passer drivers to do the best you can possibly achieve with this kind of thing. Please use the feature and then we'll see the drivers get better at it. So this is just another way of getting mobile gaming up to console-level graphics, as we keep trying to say in Vulkan. I hope you all use it. So thank you very much. I'm relying on you guys now doing this. That's me. Email me if there's a question I can't answer now. Any questions?
Seems like it would be easy to fall off the fast path doing this, as you say, because the driver doesn't do the right thing, or you set the wrong bit somewhere and the driver can't make the right decision that you expect it to. Is there going to be like a debug layer or some way that you could query and say, hey, I'm on the fast path with the current setup?
So it wouldn't be the debug layer as such, because it's whether you've fallen off the fast path would be a portability question, but I would expect that then the specific tools will tell you whether you're still working or not.
So yeah, we obviously run Pixel storage on RVR, and we certainly plan on having some kind of, unfortunately it's going to be implementation specific, but query, let's say, can ask, basically query the driver, the results of a runtime compilation and ask it how much stuff ended up on chip, when you're going to flush, etc., etc. So we're definitely going to provide that, committing to when, maybe in 5 years' time, hopefully significantly more than that. But I think it will be really difficult to do that in a completely cross-platform. I don't know, maybe we both did Pixel over storage. There might be some vendors that can cooperate, but it would still be fairly vendor specific. I think the important thing here, though, you might fall off a fast path, but you're not falling onto a slow one. In Vulkan, you opt into faster things, you don't not opt into slower things. So.
Yeah, I would hope the driver will do the best it can for this, so you may not be able to find out when you're going outside, but whether you can actually do anything about it is another matter.
Any other questions?
Any questions on the call? Anybody on the call?
All lines have been unmuted.
So, any questions on that? This was silence, thank you.
I guess maybe I will amplify a little bit on what Michael just said. Something I didn't stress when I talked about layers earlier is that Cronus is providing a bunch of them. There are at least 9 or so, I think, in the current stack, but it's not intended to be owned by us. It's open, all those are open source, and you can clone them and make your own. But we certainly expect that IHVs will do layers of their own which offer specific optimization advice based on just tracing what you're doing and commenting on it. If there's a way for us to make it cross-platform, we will. That's kind of fundamentally hard, though. But if you want to write layers, please do. It's intended to be a sandbox, and expect clever stuff to come out of the community.
All lines have been muted.
Okay, so after I've described how you might want to connect those buffer accesses together, you'll need some way of working out when everything's finished working so that you followed it. And that's what Tobias is about to tell us about.